Hello and welcome. Today, we're jumping right into one of the most fundamental topics in chemistry, the states of matter. We are going to break down how everything, from a solid block of ice to the very air we breathe, really works on a tiny particle level. So, let's get right to it.
So to get us started, here's a quick question for you. What could an ice cube, a flowing river, and a fluffy cloud possibly have in common? I mean, they look and feel completely different, right? Well, the answer is actually pretty simple. They are all made of the exact same stuff, tiny, constantly moving particles. And grasping this one simple fact is the key to unlocking everything else we're going to talk about.
And the scientific idea that explains all of this, it's called the Kinetic Particle Theory. This is our foundation for today. The big idea that explains pretty much everything that follows. Think of it as the official rulebook for how all matter behaves.
So what does it actually say? Well, the kinetic particle theory is a model that tells us two key things. First, all matter is made of tiny particles. And second, these particles are always, and I mean always, in constant random motion. The amount of energy these particles have and how they're arranged is what makes something a solid, a liquid, or a gas. It's that simple.
And that brings us perfectly to the three main characters in our story today: solids, liquids, and gases. So let's take a closer look at each one and see how the behavior of their particles makes them so different.
First up, solids. In a solid, all the particles are packed super tightly together. You can see they're in this neat, orderly pattern we call a lattice. Now, the forces holding them together are really strong, so they don't have enough energy to go anywhere. Instead, they just vibrate. They jiggle around in their fixed spots, and that's exactly why solids have a fixed shape and a fixed volume.
Okay, next up, liquids. Now, in a liquid, the particles have a bit more energy. The forces between them are weaker, and this allows them to break free from that super rigid lattice structure. They're still pretty close to each other, but now they're all jumbled up, and they can slide right past one another. This movement is precisely why a liquid can flow and take the shape of whatever container you pour it into.
And finally, we've got gases. In a gas, the particles have a ton of energy. They're basically in party mode. The forces between them are incredibly weak, almost non-existent. This means they're super far apart, and they're zipping around quickly and randomly in every possible direction. And that's why a gas will always expand to completely fill any space you put it in.
This table right here is a fantastic little summary of everything we've just discussed. Just look at the trend. As you go from solid to liquid to gas, the arrangement gets messier, the movement gets crazier, and the energy goes way up. Honestly, this is a great slide to screenshot for your revision notes.
Okay, so we know the particles are arranged differently in each state. But how do we actually get them to change from one state to another? The answer is all about energy. By adding or removing heat energy, we can literally force a substance to transform.
And this diagram shows those changes perfectly. When a solid turns to a liquid, we call it melting. When a liquid turns to a gas, that's boiling or evaporation. And it works the other way too. Gas to liquid is condensation, and liquid back to solid is freezing. Every single one of these changes is just about particles either gaining enough energy to break free or losing enough energy to get locked in place.
We can actually map out these transformations visually. To do that, scientists use a tool called the heating curve. It's basically a graph that tells the story of what's happening to the particles as we continuously add heat.
So, a heating curve basically tracks temperature as we heat something up. But this brings me to a classic exam question, something I've always wondered about. Looking at the graph, why does the temperature stay completely flat while the ice is melting? Shouldn't it keep getting hotter?
That is an excellent question, and it's something that trips up so many people. Those flat parts of the graph, we call them plateaus, are incredibly important. They show us the exact moment the substance is changing state. The first plateau is melting, where it goes from solid to liquid. The second one is boiling, where it goes from liquid to gas. So here's the crucial idea you have to remember for your exams. During a state change, all the heat energy you're adding has one specific job: to break the forces that hold the particles together. It's not making the particles move faster. And since temperature is just a measure of the average kinetic energy, how fast the particles are moving, the temperature can't go up until that job is done, and the state change is totally complete.
Okay, that makes so much more sense now. Right, here's another one that always seems to come up. We saw that both boiling and evaporation turn a liquid into a gas. So, what's the actual difference between them?
Another fantastic question. They might seem the same, but they're very different. There are two key differences.
Boiling happens at one specific temperature, the boiling point, and it happens through the entire liquid. You see bubbles forming from the bottom all the way to the top. But evaporation, that can happen at any temperature, and it only happens at the very surface of the liquid, where the fastest, highest energy particles have just enough kinetic energy to escape into the air.
All right, now that we've nailed the theory behind states and how they change, let's see how it applies to a couple of real-world things it explains perfectly: gas pressure and diffusion.
Gas pressure is really just about collisions. Think about a balloon. The billions of gas particles trapped inside are flying around and constantly smashing into the walls of the balloon. The combined force of all these tiny collisions is what creates pressure. Now, if you heat up that balloon, you give the particles more kinetic energy. They start moving faster, hitting the walls more often and with more force, and boom, the pressure goes up.
Next up, diffusion. You've definitely experienced this. Diffusion is simply the process where particles spread themselves out. They move from an area where there's a lot of them, a high concentration, to an area where there are fewer of them. It's the reason you can smell cookies baking from the other side of the house. Those smell particles are diffusing through the air to reach you.
And this image shows it perfectly. On the left, you see all the pink particles are bunched up together. But because they're always in that constant random motion we talked about, they just naturally start to spread out and mix with the blue particles. And they'll keep doing this until they're spread out completely evenly, just like you see on the right. It happens all on its own.
Got it. But it seems like some smells travel way faster than others. Does the actual size of a particle change how fast it can diffuse?
Absolutely. It makes a huge difference. And this classic experiment proves it. If you put some ammonia gas at one end of a tube and some hydrochloric acid gas at the other, they'll diffuse towards the middle. Where they meet, they react and form a white ring of smoke. But look closely. The ring forms much closer to the hydrochloric acid end. Why? Because the ammonia particles are lighter. They have a lower relative molecular mass. And so the key takeaway is simple. Lighter particles diffuse faster. And there you have it. When you really think about it, from the rigid structure of a solid to the pressure inside a car tire, to the way a scent travels across the room, it all comes back to that one powerful idea, the kinetic particle theory. It's an amazing model for explaining the world all around us.
So, to leave you with one final thought to puzzle over, we know that gas particles move at insane speeds, something like 500 meters per second. So if that's true, why isn't diffusion instant? Why does it still take a few seconds to smell something from across the room? I'll let you think about that one. Hint, what else is in the air that those particles might be bumping into? Thanks for joining me.